So first of all, I would like to thank the organizers for the invitation to present some of the work that we've been doing in Belfast on R-matrix with time dependence theory. And this theory is specifically adapted to describe atoms in strong fields. And it involves the work of quite a number of people, but the one person that I should emphasize in particular is Michael Lysaght, who is now at the Irish Center for High-End Computing, who has really been instrumental in driving this entire method forward. So what we want to do in Belfast is to describe a method that can really investigate ultra-fast multi-electron dynamics within general atoms. We're not interested in two-electron atoms, we really want to tackle general atoms and really describe atoms from first principles. Now, if we're dealing with ultra-fast processes, short times, Heisenberg uncertainty relationship, it means that we're dealing with large photon energies. And when there are large photon energies, that means that actually quite a lot of atomic physics can happen. We can excite, ionize several electrons simultaneously. We can also eject inner shell electrons, and then there's all kinds of dynamics can take place in the outer shell. So there's quite a lot of physics that we would really like to describe. But one of the problems is that there are very few methods that can actually treat general atoms in strong laser fields from first principles. Now, in Belfast, we've got a great tradition in developing methods for describing general atoms. Scattering codes, photoionization codes, they've been in development in Belfast over the last 45 years. So one of the things that we couldn't do was really ultra-fast processes. So that is one of the things that we've recently started, and the method was actually demonstrated for a one-dimensional problem 15 years ago by Phil Burke. And since then, we've actually in the last 5 years, we've developed 3 different methods for describing ultra-fast processes in R-matrix theory. The first approach was an inner region only. We'll explain what is meant with the inner region only shortly. It was developed in Belfast, but also developed in the US by the Klaus Bartschat. And more recently, we've now extended it to an inner region and outer region approach, where we've used an R-matrix propagator, and more recently, finite difference methods in the outer region. So the basic principle of R-matrix theory is a separation of space into 2 regions. We've got an inner region in which we've got n+1 electrons, and within this region we describe all interactions between all electrons. This is where the interesting, or the electron-electron repulsion is strong, and we have to make sure that we describe it in its full to its full extent. Then we've got an outer region, and at the moment we only allow 1 electron to escape from this inner region box into the outer region. This electron then feels a long-range field from the nucleus, from the remaining electrons, possibly also from the field. And what we actually do is simply propagate an R-matrix outward to some kind of large distance. In scattering process, we would match with asymptotic solutions here at the boundary. What we'll do in time-dependent approach will become clear shortly. The R-matrix that's being propagated is obtained at this inner region boundary simply through a diagonalization of the Hamiltonian, and it contains all the information that we want about the inner region. Where does the R-matrix come from? Well, the basis, of course, is the Schrödinger equation. We've got the Hamiltonian, we've got an energy, H minus E operating on psi is 0, but there's a problem if you create a box. We want to have flow out of the box, and the flow is described, basically the flow must be described through an operator, a Bloch operator, which ensures that this left-hand side here now is Hermitian. So the Hamiltonian plus the Bloch operator is Hermitian, but that means we also have to add it on the right-hand side. So we get Bloch operator operating on the wave function on the right-hand side. We can rewrite it in this form, and now we've got an equation linking the wave function to some kind of operator operating on the wave function. If we perform a diagonalization technique in the inner region, then this equation transforms into a wave function equation for the electron in the outer region, which is simply that the wave function of the electron in the outer region at the boundary is the R-matrix times the derivative of the wave function of the outer electron at the boundary. And this relationship between wave function and its derivative for the outer electron is given by the R-matrix. So that's why the R-matrix is such a fundamental quantity. If you do a scattering, you can then match it with asymptotic solutions and you can link the R-matrix to the S-matrix. Now, in a time-dependent approach, things have to change slightly. We've got a time-dependent Schrödinger equation, and in order to transform it into an R-matrix form, we use a Crank-Nicolson scheme, and we obtain an equation of the form the Hamiltonian at the midpoint of a time interval minus the energy times the wave function, or at time q plus 1, is minus the Hamiltonian plus the energy at the wave function at time step q. Now, I use the word energy, but that should be taken with a bit of a grain of salt, or a few grains of salt, because it's not an energy. This is essentially an imaginary energy, which is simply related to the time step. But if we write it as an energy, then the entire relationship with the R-matrix formalism becomes much clearer. So what we have is essentially the same equation as we had earlier, except we've got an additional right-hand side term. If we write it out in an R-matrix equation, we get the wave function Hamiltonian plus a Bloch operator minus the energy operating on Bloch operator wave function, as we had before. But now we've got this additional term, the Hamiltonian plus the energy operating on the wave function. So it's the same equations, but with an extra inhomogeneous term. And again, the Bloch operator is basically the standard R-matrix Bloch operator. It's there to ensure that the Hamiltonian in the inner region is Hermitian. If there's a field present, then we need to adapt the Bloch operator if the field is described in the velocity gauge. In the length gauge, there's no problem. In the velocity gauge, this Bloch operator needs to be extended with a field term. So if we follow the same principles, we basically get a very similar equation for the wave function of the outer region, or of the electron in the outer region. The wave function at the boundary is the R-matrix times the derivative of the wave function plus this additional vector t, this additional t vector, and this t vector describes flow from the inner region from the wave function that we know at time step q. So there are two terms, one relationship for the unknown wave function, and then there's also flow coming from the known wave function. Now, in order to solve this equation, we know that we're dealing with a time-dependent approach, and that as soon as we get to a sufficiently large distance, we know that the wave function is going to be 0, because there simply hasn't been time for the electron to get out that far. So one of the important things is that we're dealing with short times at some sufficiently large distance. The wave function for the outer region electron has to be 0. Now, that gives rise to a way in which we can actually start to solve the equations and actually obtain wave functions. We know the wave function at a large distance. The R-matrix and the t vector are obtained from the inner region diagonalization. They are known at the inner region boundary. So we know everything, how to do everything in here. Now we have to deal with the outer region. So the way that we deal with the outer region is that we divide it into small subsectors, and then we propagate the R-matrix and the t vector outwards in these small steps across all these sectors. And in order to do the propagation, what we really need is to obtain Green's functions on these sectors. And the subindex here indicates whether it's the right boundary or left boundary. So by using the Green's functions and the R-matrix on the left-hand boundary of a subinterval, we can obtain the R-matrix at the right-hand side of the interval. The same goes for the t vector, except that we now also need these j vectors, which are simply an integral over the subinterval of a Green's function, Hamiltonian plus the energy, and the wave function on that interval. It's all a lot of mathematics, but we can all, once you know what to do, it's actually quite straightforward to implement this. The bottom line is we simply need to calculate Green's functions on all of these sub-intervals. And
so,
that, yes?
This is talking about propagation in space.
Yes.
There's time as well.
Yes, the propagation in time is done using the Crank-Nicolson scheme. So that's the first thing that we start with, is basically write the equations into a Crank-Nicolson form.
Okay, so then you don't really think about time sort of after that.
You don't think
of
of,
it's just moving in R.
yes. So the real effort of the calculation is really, the time-consuming part is really into these Green's functions. So once we've got the R-matrix and the T-vector at some sufficiently large distance where the wave function can be set to 0, we then know the wave function at a large distance, and we know the R-matrix and the T-vector at all the sub-region boundaries, and now we can just propagate the F-vector or the wave function inwards. And once we've got the F-vector at the right-hand boundary of an interval and the left-hand boundary of the interval, we can then obtain the wave function across the entire interval. The equation that's used for propagation of the wave function is given here. It's getting more and more complicated, but again, it includes R matrices, Green's functions, T vectors, and these J vectors. All of this information is known. We've already calculated it. So it's just a bit of mathematics. There's no computational difficulty in calculating this expression. Finally, when we've obtained the wave function on the inner region boundary, we can then use this equation to obtain the entire wave function in the inner region. So it is, yes?
Is this scheme always stable, the propagation? I mean, it's kind of dangerous.
This is actually surprisingly stable. If we go to the other approach, which is the R-matrix time dependence approach, there it is very subtle. There you can really, it is stable as long as everything works, but if it's not stable, then it quite quickly goes horrendously wrong.
Can I ask in the same direction? Does it scheme keep unitarity during the time evolution?
This scheme keeps unitarity, yes.
This is a peculiarity of Crank-Nicolson.
Yes. In the R-matrix with time dependence, it's not as obvious that there's no reason why unitarity should be preserved. In that scheme, for calculation that we're doing at the moment, typically we've got a loss of unitarity or loss of norm of the wave function about 10 to the minus 10, which is pretty decent. So in order to operate this scheme, the first thing that we have to do is basically look at the standard R-matrix codes to obtain all the data that we need. And one of the things that is absolutely critical is accuracy of our wave functions. And the standard basis used in the R-matrix codes is fine for scattering, but for our current purposes, where we really propagate over many iterations, it's not sufficiently accurate. So we've adapted the R-matrix code to use B-spline basis sets and to get continuum functions across the entire energy range. One other thing that we needed to add was that we needed to calculate boundary derivatives, obtain boundary derivatives for all the eigenstates that we obtain inside the inner region calculation. And the reason that we need to get these derivatives is because we've got one Hamiltonian in here with a Bloch operator. Here we've got the Hamiltonian that's operating on the wave function without a Bloch operator. Now once we diagonalize, we get the eigenvalues of H plus LB. So what we need to do in the calculation is actually take the Hamiltonian, subtract the Bloch operator. And the Bloch operator is essentially a product of wave function amplitudes and wave function derivatives. In order to do that in the outer region code and get these two Hamiltonians, we also need to calculate these wave function derivatives and provide those, obtain those from the inner region codes. So we do need to modify some of the codes. They do provide a bit of extra demands on these codes. We also obtain the dipole matrix elements. We primarily propagate using the length gauge, but we can also propagate using the velocity gauge, but it's simply not as stable. For the initial state, we just said, okay, the initial state is simply an eigenfunction in the inner region. The outer region wave function is 0. And then, in order to speed up the calculation, we parallelize over processors. And typically, they're parallelized over outer region sectors. Communication between the sectors is simply the R-matrix T vector F vector. And this scheme parallelizes well up to about 200 cores. Beyond that, the sequential nature of the R-matrix T vector propagation starts to kick in and make the entire scheme less efficient. So in order to demonstrate some of the physics that can be obtained out of this approach, what we first looked at is basically ultra-fast dynamics inside the 2s 2p squared configuration. So we start in carbon plus 2s squared 2p with m equals 0. We then have a pump pulse that excites 2s 2p squared. And then after a certain delay, we've got a second pulse that ionizes from this excited configuration to just above the ground state of carbon 2+. And what we hope to see is by varying the time delay between the two pulses to see some of the dynamics that occurs within this configuration. Now, in order to visualize the dynamics, we're not going to use the LS coupled basis, but we're going to a basis, an uncoupled basis, where we've got two basis functions of 2p electrons, both with m equals 0, and two 2p electrons, one with m equals 1, one with m equals minus 1. So that the total magnetic quantum number m is equal to 0. Now the only outgoing electron that can outgoing electron must have m equals 0, because this is an S state, so total m is conserved during the calculation, so the outgoing electron must have m equals 0. And it actually occurs that photon absorption primarily goes through a resonance 2s 2p 3s, and that means that in order to excite this resonance, it is preferred that the state is in this uncoupled basis state. This basis state does not couple with this resonance. So now, if we look at as a function of time at the ionization yield, then we can see this oscillating pattern in the ionization yield. And the oscillations, or the slow oscillations, can be interpreted by looking at the population of the basis states, m equals plus minus 1 and m equals 0. And we can see that when we actually have a large ionization yield, we are in the m equals 0 basis state. When there's a lower ionization yield, we are in the m plus minus 1 ionization yield. It can also be seen that the ground state couples primarily with the m equals 0 basis state. Due to the laser field, you see these oscillations here in the m equals 0 population during the pump pulse, whereas for the m equals plus minus 1 basis, the oscillations are completely absent. And that means that there's no strong interaction.
What does the pulse look like?
It's a 3-cycle sine squared, 6-cycle sine squared pulse, both the pump and the probe.
Another question, why do you start the probe so late? It seems that you're showing only data starting at 4 femtoseconds.
The time given, I should actually, the time given here for the delay is actually at the peak of the probe pulse. The populations are as a function of time. The ionization yields are given as a function of the peak of the probe pulse, which is delayed with regard. So there's about 2 femtoseconds for the pump pulse, and then there's basically half the probe pulse has to emit or has to pass before we get our first data point. So that's why it starts a bit later.
Sorry, there's no spin orbit terms in this Hamilton?
There are no spin orbit terms. No, it's all non-relativistic. So if we have a very naive picture, then really the question is, what is actually driving the dynamics? Now, if we go very naively, 2s 2p squared, doublet s even, doublet d even, same configuration, and the only energy separation that's different, or energy interaction that actually leads to an energy separation, is this one particular electron repulsion integral. And that means that what we actually have is a 2-electron wave packet in which both electrons move in a correlated fashion, and the correlation is driven simply by the electron-electron repulsion of the 2 electrons. Now, The one thing that's not clear is that this picture is actually right, because here we can just show the ionization yield. But what we can also do is increase this probe pulse energy and go above the 2s2p triplet p threshold, in which case the outgoing electron can have m equals 1, 0 or minus 1. And if we do that and then look at several delay times and look then at what are the angular distributions of the ejected electron, we can see that when we've got this, so the first picture that we will have is at the peak of m equals 0, then we'll go to a minimum in m equals 0, peak again and then a minimum. So we have 1.5 cycle. So when both electrons are in m equals 0, we can see that the preferred directions for the ejected electrons above the 2s2p threshold is parallel to the laser orientation. Then if we increase the delay time, we get to a state where basically there's significantly less or basically none along the laser polarization. It's all at the angle of about 45 degrees. Then it aligns again along the laser direction and then moves away again. And this is in some sense a clear demonstration that what is actually seen is actually this dynamics between m equals 0 to m equals plus or minus 1 back to m equals 0. And that it really is this correlated dynamics between the two electrons. One further thing that we can do is to look at how this dynamics depends on the excitation pulse length. So we started with a 6-cycle pulse, which is 3 cycles turn on, 3 cycles turn off. And then we can see that if we've got a maximum 1 minus 1, we've got emission away from the laser polarization direction. 0, 0, we've got emission along the laser polarization axis. If we increase the pulse length, excitation pulse length to, or pump pulse length to 12 cycles, then this entire dynamical picture has disappeared because we essentially only populate the doublet as even state in this case. But if we increase then to 18 cycles, then both states again have the similar population and this dynamics reappears again. So depending on what the mismatch is between the excitation energy and the pump photon energy, we can actually vary the kind of dynamics that's occurring within the excited configuration. From an experimental point of view, one of the other things that's used looked at extensively as well is harmonic generation. And so we've recently started to look at harmonic generation within TDRM. Previously we had the R-matrix flow K code, which could do ionization in strong laser fields, but it was difficult to actually obtain harmonic generation due to the difficulty in extracting wave function information. TDRM makes it a lot easier. So questions that occur here, basically how accurate is the method actually? Is there any role of multi-electron dynamics? But also there are various operators that can be used to extract harmonic generation information. Which is actually best for a multi-electron approach like TDRM? So we've done some calculations for helium where we have looked at length, velocity and acceleration. For other atoms we are basically at the moment just sticking with length and velocity. So we can, for example, compare for harmonic generation obtained through the dipole acceleration term and compare that with harmonic yields obtained using the helium code developed by Ken Taylor. And we can see actually some differences for the fundamental, which is essentially due to the quality of the wave function near the origin. It's simply not sufficiently accurate to really get the acceleration form completely spot on. If you use dipole length, dipole velocity, everything is much better. It's simply that the acceleration emphasizes everything near the origin, where there are simply some which is simply a more difficult calculation. Once we move away from the fundamental, we see extremely good agreement between the various methods, up to well into the cutoff regime. The only place where there's a difference is in the 9th harmonic, where we can really see how a simple description, just a single target state, doesn't match up at all with the helium code. But then if we include 6 target states that are real orbitals, we get some improvement. If we go to pseudo states to improve it, we actually get very, very close to the helium code. So if we improve the atomic structure, we can really see that the TDRM method really starts to converge towards the helium, the harmonic generations obtained using the helium code, which is really a good measure of the accuracy of the approach. We've also looked at argon. In this case, we've gone at 200 and 240 nanometers and looked at how the 5th harmonic is affected by 3s, 3p6 and p resonances. So what we have here is basically the general harmonic yield comes from the emission of a 3p electron, but now there's an interference between emission of a 3p electron and excitation of a 3s electron through this np orbital. And by manipulating the states that we can include in the calculation, we can really extract what the effect of the resonances is. So the blue calculations include everything, and then the red background calculation excludes exactly these resonances and the continuum series associated with it. And we can see how the resonances start to play a role in the 5th harmonic yield. And we can also obtain resonance parameters, Q parameters, widths of the resonances, and investigate how they change depending on, for example, the pulse length and all the other parameters in the calculation. Now, there's just a few minutes left, so I quickly want to mention the RMT approach, R-matrix with time dependence approach. And this method has been developed recently primarily to increase scalability for high-end computing, and it may also be better suited for infrared fields and double ionization. And I should mention here Lampros Nikolopoulos, who really pioneered this technique for the hydrogen atom. So this is a slightly different technique in which we use a finite difference scheme in the outer region. And the way that information is transferred from the inner region and to the outer region and backward is different. In the RMT approach, information is transferred from the inner to the outer by extending the outer region grid a few atomic units into the inner region, and then we basically determine the inner region wave function on that particular grid, and then use that in the propagation for the outer region as normal. To transfer information from the outer region to the inner region, we determine time derivatives of the outer region wave function at the boundary, and then include that in the Arnoldi time propagator through inhomogeneous terms to propagate the wave function. And this all tends to get a bit more, far more sensitive to the actual parameters of the calculation, because it's not completely clear that the error terms that occur in the inner region will match up nicely with error terms induced from the outer region. It's simply a matter of trying to actually see whether it works, and surprisingly, it seems to work very well indeed. You really can get some good results out. So one of the things that we looked at first was time delays in photoionization of neon. And the way that we've calculated these time delays is basically by looking at the shift of the momentum spectra when you've got both the XUV and the infrared field present. The one problem that we had in this calculation was that there was a noticeable influence of final state resonances when we started to include 3s, 3p and 3d orbitals in the calculation. And those complicated the analysis of the shift, the accurate determination of the shifts of the momentum spectra. And that means that so far, or what I'm going to show next, has been really obtained with a very limited description of neon. We just assume that neon plus can be left in, well, 2p5 or 2s, 2p6. So emission of 2p or 2s electron only. And we use Hart Fock orbitals simply from the ground state of neon plus. If we include pseudo resonances, that's very dangerous for this kind of calculation, because we're in a region where pseudo resonances play a role. And the last thing that you really want is unphysical resonances to start to affect what your time delays are. if we put in pseudo-orbitals to improve any of these wave functions, we really get a big mess. So what we obtained for the time delays was, at the experimental energy of about 105 eV, we obtain a time delay of 10.2 attoseconds. And then if we go to lower photon energy, we see it rise up to about 27 eV at 27 attoseconds at 77 electron volt. This 10 attosecond compares to 21 attosecond obtained experimentally and 6.4 from their calculations. It compares with 8.4 attoseconds obtained by Kaifetz et al. So it really is in the same ballpark as the 6 attoseconds and 8.4 attoseconds. Maybe a little bit higher, but not really seriously so. And so it's still a factor of 2 lower than the experimental value. So to conclude, I've given a bit of flavor of time-dependent R-matrix theory and the kind of results that we obtained with this approach so far. We've compared with the helium code for harmonic generation really to demonstrate the accuracy of the method. And now we really want to, these were just the examples that we used to illustrate the method. Where do we want to go? We really need to look carefully at what is the best computational approach for obtaining the harmonic yield and which operator to use. And one of the key things that we found is that whatever works well for a single active electron approach may not necessarily work for a multi-electron approach. There are really differences between SAE approaches and multi-electron approaches. What we want to do in the future is to extend the application range of the method to longer wavelengths, increase the amount of atomic structure that we can include, and look at double ionization. And finally, we would like to explore how the techniques for atomic systems can be extended to molecules. And I want to finish with an advertisement that we hope to advertise soon for 2 lectureship positions, one in quantum information processing and one in strong field AMO theory. And if anyone is interested in more details on this, they can look on the Queen's website or contact Jim McCann at Queen's. Thank you for your attention.